Hello everyone. In this video we are going to learn about superconductivity. Okay. So have you ever seen a train flying? Would you like to reach hundreds of kilometers within a few minutes? How about if your electricity bills reduces drastically? How can we solve the world's energy crisis? All these questions, have you ever think about it? Yes, you can think about it. All these problems have one solution. If we create such a material which can solve these problems. Okay, so the one of these material is superconductor, which can solve these problems. So let us study about and let's know how it works and what it is. Okay, so let's think that what are superconductors first, and then what is superconductivity second, and its example, and first, second, and third, fourth, what is critical temperature and field. In 1911, Camelingons was working with mercury. He observed that at 4.2 Kelvin, the resistance of mercury becomes zero. Okay, so if he draw that resistance versus temperature at different temperature, he measured the resistance of mercury material. See here, at 4.2, the resistance decreases suddenly. So you can see that resistance is 0 at 4.2 Kelvin. So superconductivity is a material which shows zero resistance below a certain temperature. It shows this property called superconductivity. And this temperature is known as critical temperature, and above critical temperature and this region the material is in normal state, and below critical temperature the material is in superconducting state. He mentioned that this region is superconducting state. And then let's see the graph between resistivity and temperature. Here we are taking two curves. One is of silver atom and another is of mercury we are taking, and the silver atom is a normal metal, so its graph rho versus T is like this. And if you try to decrease the temperature with respect to resistivity, see at 0 Kelvin still its resistivity not 0 but having some value this much along y-axis. And then the graph between rho and T in mercury, see at temperature Tc suddenly its resistivity gets 0. So what can you say about this? That mercury below 4.2 Kelvin becomes superconductor, but Ag does not. And superconductor shows Meissner effect. This is one property. It must show that Meissner effect, and that means that expulsion of magnetic field must be obey in Meissner effect. And then at high temperature and high magnetic field, high current density vanish this property. Okay. Then superconductors are perfect diamagnetic should be, and then no loss in energy conduction. All these are properties of superconductor he observed in this experiment. Okay, then let's briefly see what are the properties and how it working. First is it should obey that zero resistance, or you can say that infinite conductivity as R equal to rho L by A. So as rho is 1 by sigma, so sigma is infinite here. Then second property is effect of impurity. As we add the impurity with superconductor, suppose that superconductor in 4 Kelvin, its critical temperature is 4 Kelvin, and if we add the impurity, then its critical temperature decreases, because as we add it vanishes its superconducting state. So to get again superconducting state, we have to decrease the temperature, then it will again become a superconductor. Its next property is effect of pressure and stress. So as see, this is the normal conducting material, normal conductor rho versus T graph. If we apply the pressure, it may be as a superconductor, because if we apply pressure, it try to become a superconductor at below Tc, right? And then on increasing the pressure on a certain material like cesium is the only one element that shows this property. So its Tc is experimentally found that it's 1.5 Kelvin, and its pressure is critical pressure is 110 kVAR. Okay, and the next property is persistent current. What about persistent current? That suppose when the current flows through a superconductor material ring, see here the figure, below Tc, then the loss in current value in form of heat negligible, means at 0 Kelvin or any other critical temperature, its resistance vanishes. So H is equal to I square RT, H becomes 0. That means the heat dissipation is 0, nearly 0. So hence the current flows through the ring for a longer time. The constant flow of current in a superconducting ring without any potential applied, that is persistent current, means it will flow a longer period of time once it starts. And this is persistent current. And let's see the next property. Next is effect of magnetic field. Suppose we are taking here superconductor, and a strong magnets, suppose N North Pole and S is the South Pole, we are applying like this, and then that strong magnetic field applied to superconductor below its critical temperature, the material loses its superconducting state. That means as much we tries to increase the intensity of magnetic field, it tries to vanish its superconducting state. Okay, so again we regain its superconducting state. We have to decrease the temperature, and then the critical temperature decreases from the before critical temperature. Okay, then so what is SC? SC is the minimum magnetic field which is required to destroy the superconducting state, that is called critical magnetic field. And if we try to plot the graph between SC and H and T, see here that SC is increases, then TC must be decreases, and then we As AC increases, TC decreases. So the graph is like this. Okay, and the 0 to TC, in between the state is superconducting state, and outside the TC the state is normal state. And the formula, as you know, that S equal to H naught, S equal to H naught whole into 1 minus T by Tc whole square and its whole bracket. And here H naught is the critical magnetic field at 0 Kelvin, and for a certain material its H naught is fixed, but Sc varying with different temperature T. Okay, and then let's see that the Sc which destroy superconducting not necessarily be an external magnetic field, but it may also arise as a result of an electric current flowing through the superconducting specimen itself. That means the magnetic field which is trying to destroy the superconducting state, it may not be the external magnetic field, but it can be the its own magnetic field. How this on, because the critical current is we are applying, and if we tries to increase the critical current, it will also form a magnetic field which is also try to increase. So in this way it can vanish the superconducting state. Okay, and then the next property, let's see in the next video. Okay, thank you.